Okay, well, people are coming in. Two cool new things to show you guys. One of them is, Danny sent this article. It's about a new polymer. It's a polymer. It's technically a very small molecule. We normally think of polymers as being these long chains of molecules. This is an individual molecule, but the shape of it, the shape that this thing grows in is sort of a star-shaped thing. I haven't read the actual research article from which it comes yet, but apparently the shape of this thing doesn't allow normally antibiotic-resistant drugs to survive when it's in presence with it, right? They think it's disrupting its cell walls, it's breaking it in some way. But it's a big deal because if you follow, maybe you guys are not aware of this, but the number of bacteria that are out there that we cannot kill using traditional antibiotics is large and growing, right? So they think that in the near future there will be bacteria which is resistant to the drug of last resort, which is Callistin. Callistin, I think that's the name of it. Callistin's a really, really nasty antibiotic that they developed in the 50s. And if you use it, it has all these other side effects, like it destroys your livers and stuff. So it's really bad stuff. And they only use it as the drug of last resort when nothing else works. And so what they have discovered is that there are bacteria out there, forms of strep, I think is what they are, MRSA. I think that's a type of strep. Anyways, it's some sort of bacteria where Callistin won't kill it. Now, right now, a few of the other antibacterial, what do they call them? Antibiotics that we use will kill it, but it's just a matter of time before they evolve into a strain that nothing can kill it. So what does this mean? It means that there will be bacteria that we can't kill. So people will go back to like the old days before we had penicillin, dying from, what should be minor infections that we can now kill, and we take for granted they're easy to kill. So in the world of finding things that can kill antibiotic-resistant bacteria, this is a very big deal. So who knows what's going to come of this? This is a very new finding, but basically they find that there are at least 6 strains of otherwise unkillable bacteria that just the shape of this polymer is able to kill. So that's pretty neat. You can read more about this. I'll post it in the announcements today. And the second one comes from Carl. This is pretty interesting. This is out of Maryland, I think. Somewhere in Maryland where they do this, where they've taken wood, right? They've taken wood, and I'm actually surprised that this hasn't been done before when I read the paper. All they've done is they've taken wood and they dissolve out the lignin, which is the colored chemical in wood. It's sort of a polymer that holds the wood together. So wood grows, and you all probably know this, that it sort of grows in these channels, right? So when you remove the lignin, you still have channels, but the stuff that's holding the channels together, now that's gone. You've dissolved it away. And then they pump back inside of it something that's transparent, like an epoxy, and all of a sudden you have a fairly transparent material that has these sort of channels running through it, right? So you go from a piece of wood just like this to wood, right? I guess you don't really call it wood anymore. It's now wood that's been highly engineered. You've taken out the lignin and replaced it with an epoxy, right? So you can make an epoxy puck that's going to behave very similar to this, but it won't be as strong as the wood transformed into this composite, because it doesn't have the channels present in it. So this group is now saying, well, we could use this for all sorts of things. It's got great low thermal conductivity. In fact, they make a big deal about its low thermal conductivity, saying, great, we could replace glass, which is already low thermal conductivity. So I don't think there's that big of an improvement. Glass is already, as we'll learn in a couple chapters, very, very low. But, there's some interesting possibilities. You can make skylights out of this. It's not perfectly transparent. If you look at so here's the structure, right? So they've replaced here you can still see that there's channels when they look down on it. They've just filled in the channels with epoxy. When they look at optical transmission along the direction of the channels versus perpendicular to them, that's what they're calling R and L. So here you're seeing transmittance as a function of wavelength. If you go to lower and lower wavelength, that's higher energy. It's going to absorb the light no matter what, right? So that it's not going to be transparent. Question? Oh no. But in the visible range, which is right here, and in the IR, it's going to be transparent, right? And then if you're looking down the channels, you get better transparency, almost 90%. And if you're looking transverse to them, it's maybe 75. That's not a great window, but a skylight, that's maybe not a bad gig. So interesting research. We'll see what this is going to happen. There's a CNN article that went along with it where there was a lot of hype. We'll see what happens with it. It's interesting. I'm kind of surprised it hasn't done before. All they do is they put it in like a strong base, and they dissolve it out, and then they just pump it full of epoxy. Okay, so today, a couple quick announcements. There was one homework 4, this is yours. If you don't have a grade for homework 4, but you turned one in, this is probably yours. I had no name on it. So come grab it if you don't see a grade when you think you should have one. Midterm 2 is this Friday. It's going to have one problem from midterm 1. I haven't posted the study guide yet. That'll be up by tonight. The rest of the other 2 problems will be from chapter 9 and chapter 13. My review session will be this Wednesday. I've got to go from 4:30 to 6:30 this time. I have to be home a little bit earlier. Okay? It'll be in this room, 4:30 to 6:30. Jake?
So when you say that would be a problem for midterm 1, do you mean like an exact problem from the first midterm? Or just
No. There will be one problem that covers concepts from midterm territory, right? We will not cover chapter 4, which is polymers, even though we're doing that now, because I don't want to test you on it without giving you a homework on it. So that'll be on the next midterm, midterm 3. Chris?
Can we bring both note sheets then?
2 sheets are fine. You can bring your sheet from last time, and you can bring a new note sheet. That's fine by me. Paul?
Do you record your review session?
Definitely. Yep, definitely. Anything else? Any other questions? Midterm related questions? Okay. So today we will pick up where we left off, which is talking about number and weight, average molecular weight. We'll do an example calculation of degree of polymerization. And then we're going to talk about how do you calculate the length of these things. We keep on drawing them as if they're linear. In the real world, they're not. They're like spaghetti noodles. They're kind of all over the place. So how do we figure out what's the average length since they're not perfectly straight? We'll differentiate between thermoplastics and thermosets and a couple different configurations and what are called isomers. And by the end, we'll talk about crystallinity. And if we have time, we'll actually start on chapter 5. I'm not sure how much we'll get through. So the first one, we'll start out with a clicker question. So go ahead and get logged in. And the clicker question is the following. For these 4 molecules, which of the following 4 molecules has the highest average degree of polymerization if the number average molecular weight is given? So degree of polymerization, that's N. We'll say N sub capital N. That's equal to our molecular weight on a number average divided by the Mer weight, where I'll remind you that the Mer weight is the weight of the repeating unit. So to answer this question, the approach is going to be, if I want you to figure out the degree of polymerization, I'm really asking how many of these repeat units would be present, right? So which one of these would have the highest degree of polymerization if all of these molecules had a number average molecular weight of about 250,000? So we'll do maybe 5 minutes on this question.
I don't think it's open on response where all 4 orders of carbons, right?
Good catch. And yeah, anywhere where it's not, actually everything's labeled except for on like these phenols, all these corners are carbon, and what they're not showing is that they each have hydrogens sticking off the side. Yep, those are hydrogens. Jimmy? Okay, people pretty much good? I think most of our responses are in. Phone. Okay, just a minute more. We've actually got a few more seconds. Okay, A, B, C, or D. Which will have the highest degree of polymerization? Okay, wrapping up. People think what? A, B, C, or D? Definitely C. So most people got this right. So how do we know what it was? Well, if we want the largest N corresponds to the lowest molecular weight. And just looking at this, even though chlorine's pretty heavy, the average weight of this is around 100. Right? That's around 100. And all the other ones are way higher. This was the next smallest one, I thought. And this one was like 300. Right? So the degree of polymerization will be 3 times higher for C than A. And B and D are both even larger. So they're going to be way bigger. Kylie?
Yeah, I don't think it's, we got like 1 year.
For which one? For A?
Yeah, for A is like
Oh, maybe I typoed.
115 is just the weight of the first one, not the whole degree of polymerization.
Oh, I probably did a typo. 14. Oh, I did 14 times 1. Sorry, that's a typo on my part. So what's it? Let me do that real quick. So it's 14 times 1, not 16. Sorry. 1 plus plus 16. I see. So it's actually it's 113. Good catch. Okay, so C is definitely the highest degree of polymerization. Any questions on this? On the formula? It's pretty straightforward. It just says if you know how heavy the molecule is and you know how many, the weight of each individual sort of brick that goes into making this thing, then you can figure out how many bricks there must be. That's degree of polymerization. Okay? So the next question is, can we control the degree of polymerization? Can we control whether or not we get really long molecules or short ones? Matt, question?
So, M sub n was the weight of the molecule?
Capital M sub n, that's the average degree of polymerization based off of weight, right? Or sorry, based off a number, excuse me, n. Right? So that's the weight of the whole molecule on average, right? You never have a polymer where all of your chains are the exact same length. We never have that. You always have to give it some average molecular weight. You can make it a tight or a broad distribution, right? So if you wanted a very tight distribution of long chains, how do we do that, right? So there's a few things we can do. We can control some processing variables, right? Things like temperature, things like the amount of radical catalyst that we add, which somebody mentioned last time, which in turn will control the rate of polymerization. So I think somebody mentioned last time that if you want to have very few but polymers and all of them quite long and close to the same length, what you could do is add a very small amount of radicals, right? The free radicals are your initiators, right? An initiator is the thing that takes your monomer, splits normally what is a double bond, not always, normally a double bond, which creates another free radical, and then that splits and attacks another one, right? So if you had very few of those to start with, then you might reach a point where you are limited in the number of initiators you have. And if you limit it, then you can only have one initiator for starting a chain and one initiator for ending a chain, right? So if you know that you add 100 initiators, right, then you're going to end up with 50 chains if all of those go completely to completion, right? Now, how realistic that is, you're still going to have some shorter and some longer, but that's one thing you can control to get longer molecular weight. Why do we care about longer molecular weight? We'll get to in a minute. Generally speaking, it's a desirable thing. It's not always the case, but it's generally desirable to have long monodispersed chains of polymers. Okay? Why? Here's one reason. Because the melting and the softening point, right, the temperature at which you get melting or softening is going to be proportional to the molecular weight. And a common problem with polymers already, even though we use them, common problem is that they just don't withstand temperature, right? They degrade under temperature pretty easily. So we'd like to make them operate at higher and higher and higher temperatures. One way we can do that is by getting longer and longer chains, right? So for example, that stops at about 10,000. Is 10 to the 5th 10,000 or is that 100,000? That's 100,000, isn't it? At about 100,000 grams per mole, you stop getting a benefit from making it longer and longer, right? So there's sort of like diminishing returns. It's sort of asymptotic. In fact, you saw it. It looks like this. Earlier on in this chapter, with the paraffins, you could already see it sort of reaching an asymptote, right? The paraffins, we said that they melted and the boiling point, melting point was sort of increasing, but it's reaching a limit where it's not getting any better. When you get around about 100,000 molecular weight, you're not getting any more improvements, right? So you can get better, right? So at room temperature, if your molecular weight is 100, which would be like one of these MERS basically, one of those MERS, then it's probably going to be a liquid or maybe even a gas, right? If it's 1,000, you might be in a waxy solid, and if you're between 10,000 and 1,000,000, it should be a solid. Sometimes these are called high polymers, right? They're things that you could like put in a CNC machine and actually try and mill it and machine it, right? If you put a wax in there, it's not going to stay put. It's not going to have the sort of strength to hold together during machining that you might want if you're shaping that way.
What is the big M stand for?
Big M's, that's your molecular weight. Again, that would either be number or weight average, and here we're just saying your molecular weight. Okay, what about shape then? It'd be nice to think of these. Well, first off, remind me why these things increase melting temperature and whatnot as you go to longer and longer chains. Yeah, these things, the longer they are, the more overlap they might have with a nearby chain, therefore the stronger van der Waals bonding, right? So you're going to get better bonding. And we'll get to why when you go to longer and longer, above 100,000, why don't you see greater improvement? We'll get to that in a minute. So let's talk about shape. The chain might be a long chain, right? Some things are actually rigid in long chains, like Kevlar actually is like a pretty long straight chain, right? Carbon nanotubes, when you make these things, they're long and straight. But a lot of them are not. They can actually zigzag quite a bit. So if it zigzags, it might even be able to twist back onto itself. So we know that every carbon wants to have 109.5 degrees if it's single bonded carbon, right? What we haven't said is, well, does it have to be like up at 45 and down at that degree or whatever? Or can it be rotated like in the plane, right? Could that one be in the plane of the board and the other one be pointing out? Yeah, you betcha. Could also go back in. It could do that as well. So really what you have is you have this happening. You have, if a certain bond is this way, then this one can be that, but it can be anywhere along that sphere. Like anywhere along this. is all like fair game for that next bond, right? That whole sphere, as long as the angle between the two is 109.5, it can go in not just flat, right? It can change directions a little bit. Does that make sense? Is that clear to everybody? That all the way along that are allowable possibilities. So your next one might be like right here, right? And then its chain might go in some other allowable possibility, right? So all this thing can turn back on itself just like a coiled rope can, get all tangled up. Your polymers can do basically the same thing. So if they do that, it almost becomes better to start thinking about polymers as just taking random directions, right? Where the longer the chain, on average, the size of this zigzag clump of particles gets bigger and bigger. It's called random walk, right? If anybody goes like rock climbing, if you've got a climbing rope and you have a 30-meter rope versus a 60-meter rope, the 60-meter rope takes up a larger volume than the 30-meter. Even though they're not like stacked or anything, it's just like a random clump. Just because the longer it is, the larger average volume is going to take. So we'll get to that in just a second. First off, if you could take this thing and straighten it out, right? If you could just straighten that chain out, this is as straight as you could get it, because you still have to deal with this 109.5 degree angle business, right? You still have that to worry about. Therefore, the total length of this chain, L, let me give ourselves a little more room. Oh gosh. What have I done? Sorry. The total length of our chain right here, L, is going to be equal to the number of segments, N, right, times the length of that segment, D. This is D, right, the length of each one. But then you have to take into account the fact that geometrically speaking, this thing is not straight, right? It has this bend. So you have to do sine of whatever that angle is divided by 2, right? Okay. So N is the number of molecular bonds along the chain. That's capital N, that's not small n. Small n was the degree of polymerization, right? That meant how many mer units. So if we go back to our polymers here, if this was what we're talking about, every mer unit has how many big N's in it, right? For every one small mer unit, lowercase n, how many big N, how many bonds are there along the chain length? More than one, right? You've got from here, that's half a bond, a whole bond, and another half bond. So you have 2 bond lengths per mer unit for that molecule. For this one, it gets hard because you've got this thing. I won't give you one of those, right? But if imagine these weren't here, then you've got half, you've got 1, this one, 2, 3, 4, 5, right? You have to count the length of these. I'd give you those if it was on a test or something, right? But you have to count how many bonds there are per mer unit. Does that make sense, Simone?
So if they're different atom types, would you average the bond length?
That's one way you could do it, or I could just give you the bond length of different atom types. I could say when carbon's bonded to oxygen, it's this length. Carbon bonded to carbon is this length. Oxygen to nitrogen. I could give you these things, right? So the one I expect you guys to know and memorize, like put on your note sheet, is carbon bonded to carbon is 0.154 nanometers, right? Because that's easily the most common. If I gave you polyethylene and I said it has a molecular weight of 1 million, I could say how many carbon bonds are in it if you stretch this thing out, right? You could estimate that. Danny?
So in that formula, do we multiply that bond length by how many of those bonds there are, or is that just it? That's at the end of this.
So we'll do an example of this in a second. Let's do it right now. Let's say that you've got polyethylene, right? And I've said that the molecular weight is 1 million, right? So I could ask, if I stretched out that 1 million grams per molecule out, how long would it be? That's a fair question, right? So how'd you do that? What's the approach? Like, how long would that be stretched out? What's the approach? Anybody have a thought? Why 16? That's because that's the molecular weight of the mer unit, right? Because polyethylene looks like this. It's carbon bonded to carbon. It's got hydrogen sticking out the side. So 2 carbons. Oh, no.
Yeah, like.
Oh, you could do it per. Yeah, okay. This is the normal definition of the mer in polyethylene. In this case, it's 24 plus 4, so it's 28, right? So 28 grams per mole. So we take 1 million divided by 28, and that number is 35,000 roughly. So N is approximately 35,000 So you know that there's 35,000 of these things. Therefore, what is capital N? Capital N is just then you say in a mer unit, how many bonds are there? There is half, 1, and another half. There's 2 for polyethylene. So you'd say capital N is approximately 35,000 times 2 equals about 70,000, right? So then you plug that in for your N, and you do the ND sine theta just like before.
Why is it 28 again?
12 plus 12 is 24 plus 4 hydrogens. Yeah. Okay. Any questions on this? Yeah, Matt?
So up on the, when we were going through the cover question,
Okay.
up there, so on A, it says CH2, but there's 5, so would we have to multiply those out? Would we have to have that?
Yeah, that's shorthand. You'll see that written. That means that that's CH2, that there's 5 of those in a row. Okay, any questions on this? So polyethylene's simple because it's, you know, just bonds straight along the way. If I gave you a molecule that had like something that went way off the side, like let's say it was a branched polymer that this was the repeat unit. You know, it's carbon, bonded to carbon, and that's the repeat unit, but it's got some chain out the side. When you're doing this and you're calculating capital N, which is the number of bonds along the chain, you only care about the ones along the chain direction. You don't count the ones on the branches. Okay? Any questions?
So just to complete the calculation for the L, so you take the 2 times 35,000
So L would be 70,000. And then what's our formula? The formula says you need N times D. D is the bond distance, in this case between carbon and carbon, since that's the bonds we're talking about, times sine of theta over 2. So we know that carbon is going to be 0.154 nanometers. And then that's going to be times the sine of 109.5 over 2. Okay? Danny?
That's only going to be, so if it is not carbon, would it ever be where there's carbon and something else?
Sure. I'd have to give you that information.
Okay, so if that was the case, would you just do, would you multiply by both of those in there, or how would you do that?
You'd add up the number of both, right? You'd split this equation. You'd do one equation, this L equals ND sine theta for the carbons present, and one for the nitrogens. You'd add them up.
Okay.
Now it gets a little bit harder because if you have like a double bond, then you don't have the same angle. A double bond is straight. It's 180 degrees, right? So I won't give you anything super hard on a test or anything. Okay, it's just the principle I want you to understand that if you stretched it out, just recognize it's not the total length because these things geometrically have to be zigzagging usually. That's all I want you to take away from this. The next thing is that they're never totally stretched out anyways, normally. Some polymers might, but most of them not. They're going to be doing this sort of random walk thing. So what we more care about is what is the distance from the start to the end on average. We're going to call that R. And R, an estimate of it is it's D times square root of N. Where D again is our distance between atoms, whatever the bond length is. In this case, if it's carbon, it's 0.154 nanometers. And then square root of N, where N is, again, the number of bonds along the chain backbone. Okay? Any questions? Okay. So these things can get tangled up. They can, not be straight, but they can actually be tangled. Is that a good or a bad thing? Just depends, right? If you have a material that is tangled up, then as you pull on that chain, you're not only stretching the bonds along the backbone, but you're also stretching whatever it's tangled up with. And that can give rise to huge elastic responses, right? So rubbers, for example. So we've got two examples here, just two polymer materials, right? These balls. And when I drop them, see the difference that they have. They're very, very similar. If you look at the molecular weight of these, one has 4 carbons and a chlorine, a couple hydrogens. The other one's got 5, 6, 7 carbons, right? So their molecular weight is actually going to be pretty similar. So their degree of polymerization is the same. So the bond length, like the chain length, should be pretty similar on these things. So why is it so different? Why does one bounce and the other one just thuds, right? What's going on there? Any thoughts? If you wanted to engineer a material based off of what we've said, what might you do to change the elastic response? One thing is what we just said. You could have them be wrapping around each other. Let's assume that that's not the case for a minute. What could you do?
Something with more double bonds. That doesn't,
Yeah, why do you think double bonds would play a role?
it'll fix the position and won't allow it to go up.
That's really the right answer. The more double bonds there are, double bonds can't rotate, right? Not as easily anyways. They have some degree of rotation, but it's actually really limited. Single bonds can rotate a lot. So the one of these that doesn't bounce back, so this one that doesn't bounce back, it has mostly single bonds, and it has a big chunky side group. So what happens is that when you drop it, that big chunky side group can just shift. It can rotate, and in doing so, that absorbs a lot of energy, right? Because it literally moves around. Whereas this one, it's pretty rigid. It doesn't have a way to dissipate energy. So that energy, if it's not dissipated, it goes back up into kinetic energy, bounces back up again, right? It restores it back to some potential energy. Okay? So we basically what they do, and you could also achieve the same thing via cross-linking. So if you want a rubber tire and you want to make the chains stick to each other a little bit more, you can do something called cross-linking. So cross-linking, if you've got chains of polymers, right? And I think we mentioned this the other day. You've got chains of polymers. If you'd like them to tangle a little bit more, you can bond them together, right? So this would be like a sulfur group is a common thing that they use for these. Let me draw that. Right? They'll have sulfur either on the side, or they'll replace one of the carbons. They'll take it out and they'll put in a sulfur there. I lost my chain. Right? They'll put a sulfur where a carbon was, because sulfur can make 6 bonds, so it can have the 4 that it normally has, plus it can make extra ones to reach out and grab other chains. Anything you do that causes one chain to have more than a van der Waals interaction with a nearby chain is cross-linking. So the polymers that, the self-healing rubbers that we showed you in class last time, they achieve this in a really, really remarkable way. What they're doing is still a type of cross-linking, but this is how it works. It takes something that has like a very ionic charge here, and it takes something else that has an ionic charge of the opposite type over there. So it's an ionic interaction as opposed to a covalent one. Normally when you add sulfur to a natural rubber and you vulcanize it, which is how they get rubber tires, it's sulfur bonded to carbon, which is a strong covalent bond. What they do is, I'm writing this as just a plus sign and a minus sign. It's more complex than that. It's a group of atoms here and a group of atoms here that on average have a positive or a negative sign, and those interact ionically. And what's great about those is that if you pull it apart, it's just Coulombic attraction, right? The closer they get, the more that bond gets strengthened. So when you pull this thing, if you cut this, these things get temporarily separated. And if you have enough of these all over the place, it doesn't matter if you line it up exactly, because they're free to rotate a little bit. If you bring it back together, it's going to find a negative one, is going to find a positive one, it's going to rebond again, right? Because it's just an ionic interaction, which is pretty clever that they came up with a way to do that. In the back, question?
So the cross-linking make it bouncy?
Cross-linking makes it bouncy because what it does is as you deform a material, think of that as stretching one of your chains. But as you stretch that chain, it's dragging other chains sort of along with it. And so you're adding up an elastic force from more than just the one chain, because it's dragging other ones, and those ones want to go back. So it restores it, and it's not permanent deformation, it's an elastic deformation, so it bounces. Okay? So this obviously has tons of implications. If you could take the same starting material and just cross-link it, you could go from a material that absorbs energy like crazy or doesn't, right? So bumpers on your car. You could think about whether you want to absorb energy there or not, right? All sorts of applications where you want to think about how, if you want permanent deformation or non-permanent deformation, right? You can control that with the degree of cross-linking, okay? Okay, molecular shape. There's more than one type of shape. The most common one that we keep on drawing is linear, meaning, right, these things are just lined up and we just keep on drawing it. In the real world, there's also branched, cross-linked, and networked. Branched means that you've got branches that might be like a non-trivial length. They might be really long going out the side. They could be 100 grams per mole out the side, right? You can have cross-linked, which we just showed you, and then networked. Networked, what's the difference between cross-linked and networked? Thoughts? Where have we heard networked already? We talked about it with one of the polymers. It was this one. The Bakelite, we said, was a network polymer, right? And if you remember how it worked, it's this molecule. So these are just hydrogens, or methyl groups, actually. But these ones can have another covalent bond in one direction, a covalent bond in a second direction, and a covalent bond in a third direction. So it can have covalent bonding in 3 directions. So you can form a 3-dimensional structure as opposed to just a line, basically. Okay? So that's different than cross-linking. It's not the same as cross-linking. Cross-linking has to do with long chains that you just knit them together at certain points. A network polymer, it's not chains anymore. Okay? Okay, molecular configurations. So we had these MER units, right? The MER unit is one that gets repeated over and over and over. It doesn't always have to have the same configuration. So sometimes they'll call it head and tail, right? So imagine this is our repeat unit. It looks like polyethylene, except we've substituted one of the H's for R, which means it's some group. If it's chlorine, then it's polyvinyl, like PVC, it's polyvinyl chloride, right? If it's a methyl group, then that's polypropylene and so forth, right? So the question is, does it have to be no radical, radical, no radical, radical, right? If that's the case, then it's head to tail, right? Radical, no radical, and so forth, right? However, if you've got no radical, radical, and then the next MER starts with a radical, it's still, polypropylene or polyvinyl chloride, but it's a different, we'd say different configuration, right? Because in one configuration, you've got the side groups next to each other, and the other one, they're not next to each other. First off, would they want to be next to each other? Energetically, no. How come? Because generally side groups are bulky, they're going to have some volume, and if they occupy the same space, it's just like our hard sphere models. You get electrons occupying the same volume, which they can't do without costing energy. So if it's a really big side group like styrofoam had the big benzene ring sitting off the side, it's very unlikely that you're going to get head-to-head configurations on that, because that benzene ring is going to be too big to stack next to each other, okay? And then you can also have tail-to-tail, right? You have isomerism. Isomerism means that there's different ways you can arrange these things, right? So you can have stereoisomerism, which is either isotactic, syndiotactic, or atactic. Isotactic means if you have a side group, it's always on the same side. This is isotactic, right? This is styrofoam, right? This is polystyrene. If it was expanded, it would be styrofoam. This is polystyrene as it's drawn right here. And they're all on the same side. Or you could have syndiotactic, which means it's alternating, or atactic, meaning it has no preference. Styrofoam, you might expect it to be syndiotactic because it does your best chance of separating these groups, right? Overlap is going to cost energy, generally speaking, so this is probably the most lower. If you could calculate the energy of these things, this is probably, I'm guessing here, the lowest energy one. I don't know that. I would guess that, okay? You can also have geometric isomerism. Again, isomer is just different ways of having the same structure, or same compound in different structures, changing the structure slightly. This is cis versus trans. So if you have a double bonds, remember now these are rigid, right? If your chain is both on the same side, let's say on the bottom side, we call this cis, right? But if they're on opposite sides, it's trans, right? So cis and trans. I think we've already mentioned thermoplastic versus thermoset a few times. A thermoplastic is something that's basically just van der Waals bonds holding it together. Therefore, when you heat it up, you can overcome those van der Waals bonds without necessarily decomposing it. It means you can melt it and do melt processing. That's one of the reasons why we use plastics, because you can cast shapes like this with injection molding really, really easily. Because all you have to do is just melt it, squirt it into some cavity, and let it cool down, and you're stuck with your shape. It's very convenient compared to working with, say, ceramics or even some metals. Thermosets are different. They might be liquid when you start, right? It might be molten when you first are making it, but once it sets up, once either cross-linking occurs or network forming occurs, it's now covalently bonded. The chains aren't van der Waals bonded, they're covalently bonded. So to break it, you've got to break a covalent bond. When you do that, when you break a covalent bond, it releases a lot of energy, which might cause this thing to actually just keep on breaking bonds, and it's just going to burn, right? It doesn't flow necessarily, right? And the number here to have in mind is something like 10 to 50% of the MER units are cross-linked for it to become a thermoset. So rubber we know doesn't melt, it just burns. So if you start cross-linking, between 10 and 50%, you're going to start to expect thermoset behavior, which can be good. A thermoset's good in terms of keeping its shape. If you want to put something in the CNC and actually cut something out of it, you don't want to try and cut a rubber band because it's just going to deform too much. But a hard rubber you can cut no problem. Okay, we talked about polymers. There's also such thing as copolymers. Copolymers means that instead of just having the same MER unit repeating over and over, and note even the MER unit can change, right? Because it can be cis and trans, it can be head to tail, it can be on the same side, other sides, right? So there's isomers, but you could have different MER units as well, right? So these are called copolymers. So if you have A and B, which are different copolymers, maybe you've got a polyvinyl chloride MER unit, and followed by that you've got a propylene. So now you've made a copolymer blend of propylene, polypropylene, and polyvinyl chloride, which probably has some name, right? So you can arrange those polymers in different ways. You could alternate, like A, B, A, B, A, B. you could do sections, right? You could have A followed by a bunch of B's. This is kind of just random, actually. You could have big section of B, big section of A. You could have the backbone is A, but the chains going off the side are B, right? So these are called nothing. There's no name to it. This is just pure polymer. You could have alternating, random, block copolymers, or graft copolymers, right? And there's some important examples, types of rubbers that have these. For example, you've got a styrene group and a butadiene group. So SBR rubber is styrene butadiene. You've got two different copolymers that come together to make that polymer have the properties it have. Or acrylonitrile butadiene rubbers, like they make gloves out of these. Okay, let's talk next about polymer crystallinity. We've been describing this as terms of a climbing rope, right? So who goes rock climbing? Fair number of people in Utah. This is a pretty common thing. So it used to be the case that coiling a rope was a big deal. It used to be really like, you didn't see rope bags as often. Coiling ropes was like the traditional way to do it. And when you do that, you'd stretch this thing out, right? You'd lay it over your neck. You'd reach over, you'd stretch out another leg. You'd lay it over your neck. You keep on doing this and you get this big sort of aligned section. It's about an arm length, right? I'm about 5'6", so it's about 5'6" or whatever of rope, right? And for that 5 feet 6 inches roughly, they're lined up. It looks kind of crystalline, right? So that's exactly what happens with polymers. You get sections of it which line up to each other and become kind of crystalline. Just like a coiled rope looks kind of crystalline, right? So how it kind of looks is you've got sections like this, right? And then it might be non-crystalline, and then you might have another section which is relatively crystalline. It's just like coiled ropes, right? So the question I asked earlier, if you make these molecular weights longer and longer, over 1 million, why don't you get stronger and stronger bonding? Why doesn't it just lead to higher and higher van der Waals forces? The problem is you're not ever stacking these things linearly. They're always breaking into smaller chunks like this, right? So if you get to 1 million, it doesn't matter. You've just got more and more chunks of these things, right? It's not like the whole thing's getting longer sections themselves, right? So we'd say that this is sort of the crystalline region. This is the amorphous, right? So crystal, this is amorphous. I think we have some pictures of this. Yeah, so there's some terms for it. You've got the micelle, and they'll call it fringed micelle. So the crystalline regions are the micelles, and then you've got the randomness connecting these things together, right? And in a polymer, this might be, if you could actually have a microscope where you could see the strands, it might look something like this, where you certainly got regions where it looks kind of ordered and regions where it's just not very ordered, right? This looks kind of like a grain and a grain boundary when we think about the crystal structure we've been talking about. You see things kind of like this in polymers. And in fact, you can even start calculating the density, right? You can calculate the density and use that to tie it into the crystallinity. So within, let's give ourselves some room. Let's say within a unit cell, we could have like a tetragonal unit cell. You could know that like the chains line up in a very specific way in here, right? The chains might line up in a very specific way. You've got some unit cell within your micelle region. I could actually give you A, B, and C, and I could say how many MER units fit inside of that, right? I could say that Z, the number of MER units, is given, and you could calculate the density, right? Again, this is only for the crystalline, thank you, I've asked, right? You know the density within that crystalline region. This is straightforward enough. It'd be just like calculating density before, our theoretical density calculations, except now instead of Z being the number of formula units, it's the number of MER units, right? Fair enough. In the real world, this would be for a completely 100% crystalline polymers, which is very, very rare. In the real world, you're going to have something less, right? So what they do is they use density as a measure of the crystallinity of polymers. They say the percent crystallinity of your polymer, is it 100% or 90 or 60 or 0, right? You can figure that out because the density of the crystalline section, that's rho C. Rho S, that's the density of your sample, minus rho A, that's the density of the amorphous, if it was completely amorphous. So that is completely amorphous. And this is crystalline. If you know the crystalline and the amorphous values, and a lot of these are published, like they're known for different materials, all you have to do is measure your sample, plug it into this little formula, and it spits out your percent crystallinity, right? Which is a pretty handy thing to know. Because the more crystalline a polymer is, the more it behaves kind of like the solids, right? The less crystalline it is, the less it can behave like them. So you get stronger bonding, higher melting points, better strength out of the things that are more crystalline, okay? And there's things you can do to change the crystallinity, right? So how do you go between this and that? There's things you can do, right? So slowly cooling through the melting point allows for better packing. Why should that be the case? Why should it be that if you slowly cool it, you have a better chance of getting a crystalline polymer? Any thoughts? So turn to your neighbor, take a stab. Like, why is it if you slowly cool it, you might get a more crystalline polymer? Okay, what do we think? Let me pick on someone in the back. Let's do, I'm not calling ever. Is it Daniel in the Utah jersey? What do you think, Daniel? If you had to take a guess at this, why might you expect better crystallinity as you cool something down slowly from its melting point? What you said at the end, there's the key thing. Colder, there's less movement, right? When this thing's now solid, how easy is it for the chains to move around? Not as easy as when they're liquid. So if you cool it down slowly, assuming that there's a thermodynamic driving force for it to crystallize, which there is oftentimes, then the more mobility you give it for these chains to sort of wrap around and find the way where they're lined up to each other, the better. So cooling it down slowly that's exactly right. You get better mobility, right? If you have a material that has complex MER structures, so like a big old styrene or like a long chain going off the side or something, those things are harder to get them to line up nicely, and therefore they're harder to crystallize. So things like polyethylene, polytetrafluoroethylene, Teflon, these crystallize super easy because their side groups are just like hydrogens or fluorines, right? So you can cool them down quickly and they still crystallize pretty well. In fact, you can get almost 100% crystalline polyethylene and Teflon, right? So we'd say that linear structures are more likely to crystallize than ones that have big branches. We'd say networked, cross-linked, or branched are all going to be very bad. They'll probably be purely amorphous. Because imagine you're trying to make the chain line up on itself, but if it's connected with a bunch of cross-linking things all over the place, you can't make it form these nice micelle regions, right? You can't make it do it. And then obviously, as far as stereoisomers go, this is a very common test question I frequently look at. I say, if you have atactic, syndiotactic, or isotactic, which one would you expect to be more crystalline? You go up here and you say, well, which one of these three here is most likely to be crystalline? The one that can stack together better. So it's definitely going to be this one. This should have the highest crystallinity. This should be maybe your next highest, and this will be your lowest crystallinity, right? Because it's all about trying to make these chains lie next to each other in some organized fashion. Okay? And again, obviously, large, bulky side groups will also reduce crystallinity. Okay, so polymer crystals, if you can call them that, they're still a pretty active area of research, right? They keep on modifying the theory, right? Modern theory actually suggests that there's regular-shaped thin platelets that are about 10 to 20 nanometer in terms of their crystalline regions. They used to think that they grow just like random chunks all over the place. Now they think that they grow radially outwards in what are called spherulites. So this thing, it kind of starts here and it seems to be radiating outwards in terms of how they grow. But it's still an open area of research. Like this is very much like, still active material science research is happening here. Okay, that's chapter 4, polymers. Any questions? There's so much more to polymers. We really just gave you like a taste of some of the important ones, but there's way more here. We got a few minutes left though. Simone?
So when you were talking about seed crystals a week ago, so this like area of research, where it stems out radially, does that have something to do with like being a seed crystal?
It's a great question that I don't know the answer to. Do they use seed crystals to cause polymers to enhance their crystallinity? I would really guess that the answer is yes, but I don't know that for sure. Any other questions? Should we call it a day? Call it a day. Or one more question in the back.
Could you just talk again really quick about how you said for the van der Waals, when you're talking about how they wrap around? Now, what did you say about
Let's start on that next time.